Subscribe to the channel so you don't miss out on any of these videos. Imagine two colossal black holes, each millions of times more massive than our Sun, hurtling toward each other in a cosmic dance that has been choreographed for billions of years. They spiral closer and closer, dragging space and time into a swirling vortex around them. Then, in a fraction of a second, they collide with unimaginable force, merging into a single, even larger black hole. This violent union sends ripples through the fabric of the universe, gravitational waves, traveling across vast distances at the speed of light, carrying the echoes of this celestial clash to us here on Earth. This is the story of black hole mergers, cosmic collisions of unimaginable power, mystery, and significance. What makes these events so incredible isn't just their sheer scale or the fact that they involve the most extreme objects in existence. It's also that until recently, we had no way to detect them. But now, thanks to advances in technology and a deeper understanding of the universe, we're finally able to eavesdrop on these colossal collisions and learn about some of the most hidden and powerful events in the cosmos. Black hole mergers might sound like something ripped straight out of science fiction, but they are very real. In fact, they're happening all the time, scattered across the vastness of the universe. Yet, the idea that we could detect them, let alone understand them, is incredibly new. Gravitational waves, the key to observing these mergers, were only confirmed to exist in 2015, a discovery that earned the Nobel Prize in Physics. That wasn't just a breakthrough, it was a revolution in how we see the universe. For the first time, we could hear the cosmos through the faint but distinct whispers of these waves. So what exactly are black hole mergers? How do they work? And why should we care? Let's dive into the details, unraveling everything from the formation of black holes to the mind-bending science of gravitational waves. Along the way, we'll explore how these mergers give us a glimpse into the universe's most extreme environments, and might even hold the answers to questions we've been asking for centuries about space, time, and the nature of existence itself. To understand black hole mergers, we first need to talk about black holes themselves. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars run out of fuel and collapse under their own weight, creating a singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding this singularity is the event horizon, the point of no return, where the pull of gravity becomes inescapable. Black holes come in different sizes, from stellar mass black holes a few times heavier than the Sun to supermassive black holes that sit at the centers of galaxies, weighing millions or even billions of times as much. But even though black holes are often thought of as cosmic loners, they aren't always isolated. In fact, many black holes exist in pairs, orbiting each other in what's known as a binary system. These binary black holes are the starting point for mergers. Over time, as the two black holes orbit each other, they lose energy through a process called gravitational radiation. Essentially, they send out tiny ripples in the fabric of spacetime, slowly spiraling closer together as they shed energy. This can take millions or even billions of years, but eventually, they get close enough that their gravitational forces pull them into a collision course. The final moments before a black hole merger are some of the most extreme events in the universe. As the two black holes spiral toward each other, they accelerate, reaching speeds close to half the speed of light. The energy they release during this process is mind-boggling. In the last fraction of a second before they merge, they can emit more energy in the form of gravitational waves than all the stars in the observable universe combined. Then, in a flash, they collide and merge into a single, larger black hole, sending out a final burst of gravitational waves that ripples across the cosmos. These gravitational waves are the key to detecting black hole mergers. But what exactly are they? To put it simply, gravitational waves are ripples in spacetime caused by the acceleration of massive objects. Imagine throwing a rock into a pond. The ripples that spread out across the water are like gravitational waves spreading through the universe. Albert Einstein first predicted their existence over a century ago, as part of his general theory of relativity. But it wasn't until 2015 that we were able to detect them directly. That historic discovery came thanks to an experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses incredibly sensitive instruments to measure tiny distortions in spacetime caused by passing gravitational waves. When a black hole merger occurs billions of light-years away, the gravitational waves it produces travel across the universe, eventually reaching Earth and causing faint but detectable vibrations in LIGO's detectors. The first detection of gravitational waves from a black hole merger, known as GW150914, was a groundbreaking moment. It confirmed not only that gravitational waves exist but also that black holes can and do merge. Since then, LIGO and other observatories like Virgo and Cagra have detected dozens of black hole mergers, each one offering new insights into these mysterious objects and the universe as a whole. One of the most exciting things about black hole mergers is what they can teach us. By studying the gravitational waves they produce, scientists can learn about the masses, spins, and distances of the merging black holes, as well as the properties of the final black hole they form. These observations have already revealed surprises, such as black holes with unexpected masses or spins that challenge our understanding of how they form and evolve. But black hole mergers aren't just about understanding black holes themselves. They also have implications for some of the biggest questions in physics and cosmology. For example, they can help us test Einstein's theory of general relativity in extreme conditions, search for evidence of new physics, and even explore the possibility of hidden dimensions or other exotic phenomena. They might also shed light on the origins of the universe itself, as some theories suggest that black holes could have formed in the early moments after the Big Bang. What's more, black hole mergers are just one part of the bigger picture of gravitational wave astronomy, a field that is still in its infancy but has the potential to revolutionize our understanding of the universe. In the future, more advanced detectors and observatories will allow us to detect even fainter and more distant gravitational waves, opening up new windows into the cosmos. We might even be able to detect signals from supermassive black hole mergers or other exotic events like neutron star collisions or cosmic strings. As we continue to study black hole mergers and gravitational waves, one thing is clear: we are just beginning to uncover the secrets of the universe's most extreme events. Each new discovery brings us closer to answering some of the biggest questions in science, while also reminding us of the vastness and complexity of the cosmos. The detection of black hole mergers has not only confirmed our theoretical understanding, but also opened entirely new avenues of exploration. For example, one of the most fascinating aspects of studying black hole mergers is understanding how these systems come to exist in the first place. After all, for two black holes to merge, they first need to form as a binary pair. But how does this happen? And why do some black holes end up isolated while others end up in pairs, destined to collide? Astronomers have identified several possible pathways for the formation of binary black holes. One possibility is that they originate from massive binary star systems. In this scenario, two stars orbit each other for millions of years, both evolving and eventually collapsing into black holes. If their orbit remains intact after the collapse, the two black holes will continue to orbit each other, gradually losing energy through gravitational radiation until they merge. Another possibility is that binary black holes form in dense stellar environments, such as globular clusters. In these crowded regions of space, stars and stellar remnants are packed so closely together that interactions and gravitational encounters are common. Over time, these interactions can lead to the formation of binary systems, including pairs of black holes. This process, known as dynamical capture, might explain some of the more unusual black hole mergers detected by LIGO and Virgo, such as those involving black holes with unexpected masses or spins. There's also the intriguing possibility that some black hole mergers involve primordial black holes, hypothetical black holes that formed in the very early universe, before stars and galaxies existed. If primordial black holes do exist, their mergers could provide valuable clues about the conditions of the early universe and the nature of dark matter, which some theories suggest might be made up of these ancient black holes. The diversity of pathways leading to black hole mergers highlights just how complex and varied the universe is. No two mergers are exactly alike, and each one carries its own unique story, encoded in the gravitational waves it produces. By analyzing these signals in detail, scientists can learn not only about the black holes themselves but also about the environments in which they formed. For instance, the spins of the merging black holes can reveal whether they were born as a pair or came together later in life. If the black holes' spins are aligned with each other, it suggests they formed from a binary star system. But if their spins are misaligned, it could indicate that they were brought together through dynamical interactions in a dense stellar environment. Similarly, the masses of the black holes can provide clues about the stars they originated from, as well as the processes that influence their evolution. Beyond individual mergers, the growing catalog of detected events is helping scientists piece together a larger picture of black hole populations across the universe. By studying the distribution of black hole masses, spins, and other properties, researchers can test models of stellar evolution, explore the effects of metallicity on star formation, and even probe the role of cosmic events like supernovae and gamma-ray bursts in shaping the universe. But the story doesn't end with the black holes themselves. Black hole mergers also have profound implications for our understanding of spacetime and the fundamental forces of nature. For example, they provide a unique opportunity to test Einstein's theory of general relativity in extreme conditions. According to general relativity, the gravitational waves produced by a merger should have specific characteristics, such as a predictable frequency and amplitude. By comparing theoretical predictions with actual observations, scientists can test the limits of the theory and search for any deviations that might hint at new physics. So far, general relativity has passed these tests with flying colors, but that doesn't mean the search is over. In fact, some physicists hope that black hole mergers might reveal subtle effects that could point to the existence of extra dimensions, modifications to gravity, or other phenomena that go beyond our current understanding. For instance, certain theories of quantum gravity predict that black holes might leave behind exotic remnants or produce gravitational waves with unique signatures. Detecting such signals would be a groundbreaking discovery, offering a glimpse into the fundamental nature of reality. Another area of active research is the role of black hole mergers in the evolution of galaxies and the large-scale structure of the universe. Supermassive black holes, which reside at the centers of galaxies, are thought to grow through a combination of accretion, feeding on gas and other material, and mergers with other black holes. When two galaxies collide, their central black holes can form a binary system, eventually merging into an even larger black hole. These supermassive mergers are expected to produce gravitational waves with much longer wavelengths than those detected by LIGO and Virgo, requiring a different type of observatory to study them. Projects like the Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave detector, aim to detect these low-frequency waves and provide insights into the history of galaxy formation and evolution. By studying the mergers of supermassive black holes, scientists hope to learn more about the processes that drive galaxy growth, the distribution of matter in the universe, and the mysterious force known as dark energy, which is causing the universe to expand at an accelerating rate. But even as we look ahead to future discoveries, there are still plenty of mysteries to unravel about the black hole mergers we've already observed. For example, some mergers have involved black holes with masses that fall into the so-called mass gap, a range of masses that theoretical models struggle to explain. Understanding how these black holes form and evolve could lead to new insights into stellar physics and the life cycles of stars. Similarly, the detection of mergers involving unusually massive black holes has raised questions about the upper limits of black hole formation. Could these giant black holes have formed directly from massive stars? Or do they represent the products of multiple previous mergers? And what does this tell us about the environments in which they formed? As scientists continue to analyze data from LIGO, Virgo, and other observatories, they're also developing new techniques to extract even more information from gravitational wave signals. Machine learning and artificial intelligence are playing an increasingly important role in this effort, helping researchers identify faint signals buried in noisy data and make sense of the complex patterns encoded in the waves. The potential for discovery in this field is virtually limitless. With each new detection, We gain not only a deeper understanding of black holes and gravitational waves but also a greater appreciation for the vast, interconnected web of phenomena that make up our universe. Black hole mergers are more than just isolated events. They're windows into the most extreme and fundamental aspects of existence, from the nature of spacetime to the origins of the cosmos. The implications of black hole mergers reach even further into the unknown, touching on questions about the very fabric of the universe and its ultimate fate. These cataclysmic events, while immensely violent, also reveal the intricate dance of cosmic forces that shape reality on both large and small scales. The ripples they create in spacetime tell a story that transcends their immediate impact, opening doors to mysteries yet to be solved. One fascinating area of exploration is the energy released during a black hole merger. When two black holes collide, they emit an astonishing amount of energy in the form of gravitational waves. In some cases, this energy can exceed the total output of all the stars in the observable universe during the brief moment of the merger. This raises profound questions about how such massive energy transformations influence their surroundings. Do these waves have any detectable impact on the interstellar medium they pass through, or are their effects purely confined to spacetime itself? Moreover, the study of black hole mergers has shed light on the enigmatic phenomenon of black hole kicks. During a merger, asymmetries in the gravitational wave emission can impart a recoil velocity to the newly formed black hole, effectively kicking it across space. These kicks can reach speeds of thousands of kilometers per second, potentially ejecting the black hole from its host galaxy entirely. Observing and understanding these events could reveal crucial details about the dynamics of galaxies and the role of black holes in their evolution. The idea of black hole kicks also introduces a more speculative but captivating line of inquiry. What happens to ejected black holes? If a kicked black hole is flung into intergalactic space, it becomes a rogue black hole, traveling through the cosmic void without a galaxy to call home. Detecting these rogue black holes is an enormous challenge, as they emit no light unless actively feeding on matter. However, their existence could have implications for our understanding of dark matter, as their gravitational influence might be detectable through its effects on nearby stars or gas. Beyond individual events, black hole mergers also provide a unique lens through which to study the large-scale structure of the universe. Gravitational waves from distant mergers carry information about the expansion of the universe, allowing scientists to probe the nature of dark energy. By measuring the redshift of electromagnetic signals associated with mergers, such as those involving neutron stars, and comparing them to the gravitational wave signal, researchers can construct a cosmic distance ladder that offers an independent way to determine the rate of cosmic expansion, known as the Hubble constant. Interestingly, discrepancies have already emerged between measurements of the Hubble constant using different methods, leading to what some scientists call the Hubble tension. Gravitational wave observations could help resolve this tension, offering new insights into the nature of dark energy and the fate of the cosmos. Are we headed toward a big freeze, where the universe continues expanding indefinitely, or could gravitational waves reveal clues pointing to a cyclical, or even more exotic cosmic destiny? Another frontier in black hole merger research is the hunt for electromagnetic counterparts, visible, X-ray, or radio emissions associated with gravitational wave events. While black holes themselves emit no light, their mergers can interact with surrounding matter in ways that produce detectable signals. For example, if a black hole merger occurs in a dense environment filled with gas, the collision could trigger powerful shocks or accretion events, producing bursts of electromagnetic radiation. The detection of such counterparts would provide a wealth of additional information, including precise localization of the merger and insights into the environment in which it occurred. This, in turn, could help scientists better understand the origins of binary black hole systems and refine their models of stellar evolution. It might also offer clues about the mysterious role of black holes in driving phenomena like gamma-ray bursts, some of the most energetic explosions in the universe. As if these questions weren't compelling enough, the detection of gravitational waves has also sparked interest in searching for entirely new types of cosmic phenomena. For instance, some theories predict the existence of exotic objects like boson stars or gravastars, which could mimic black holes but behave differently in extreme conditions. Observing mergers involving these objects could challenge our understanding of gravity and the nature of matter, opening the door to groundbreaking discoveries. Then there's the tantalizing possibility of detecting gravitational waves from events beyond our current observational capabilities. While LIGO and Virgo are designed to detect stellar mass black hole mergers, other instruments like pulsar timing arrays and the upcoming LISA mission are targeting different frequency ranges. These observatories could reveal mergers of supermassive black holes, collisions between neutron stars and black holes, or even signals from the early universe, such as those produced by cosmic strings or phase transitions in the primordial plasma. The idea of probing the early universe through gravitational waves is particularly exciting. Unlike electromagnetic radiation, which is scattered and absorbed by matter, gravitational waves travel virtually unimpeded through the cosmos, carrying information from the earliest moments of the Big Bang. Detecting these primordial waves would provide a direct glimpse into the birth of the universe, potentially answering questions about its origins, inflationary expansion, and the nature of spacetime itself. Even as we marvel at the discoveries made possible by gravitational wave astronomy, it's worth remembering that we're still in the early days of this revolutionary field. The first detection of a black hole merger occurred less than a decade ago, yet the pace of progress has been extraordinary. Each new observation brings with it fresh insights, challenges, and opportunities, fueling a sense of wonder and curiosity that drives scientists to push the boundaries of what's possible. But perhaps the most profound aspect of studying black hole mergers is the perspective it offers on our place in the universe. These events, occurring billions of light years away, remind us of the vastness and complexity of the cosmos. They challenge us to think beyond the limits of our everyday experience, to confront questions that have no easy answers, and to embrace the mysteries that make the universe so endlessly fascinating. In a sense, the study of black hole mergers is a testament to the power of human ingenuity and imagination. Through the combined efforts of thousands of scientists, engineers, and visionaries, we've developed the tools to listen to the whispers of the universe, to decode the messages carried by gravitational waves, and to uncover the secrets of the most extreme objects in existence. And as we continue to explore this frontier, one thing is certain: the story of black hole mergers is far from over. The ongoing exploration of black hole mergers not only fuels our understanding of astrophysical phenomena but also drives technological advancements. The detectors like LIGO, Virgo, and CAGRA represent some of humanity's most intricate engineering feats. These observatories are so sensitive that they can detect distortions in spacetime smaller than a fraction of a proton's diameter. This level of precision has spurred innovation in fields like laser technology, quantum mechanics, and materials science, with applications that extend far beyond astrophysics. For instance, the techniques developed to isolate and mitigate noise in gravitational wave detectors have found uses in precision measurement instruments and medical imaging technologies. The pursuit of understanding black hole mergers is not confined to the stars; it has tangible benefits here on Earth. Every refinement to our detection methods brings us closer to deciphering the faintest signals, allowing us to hear the whispers of black holes merging even at the edges of the observable universe. Speaking of the universe's edges, black hole mergers might also provide insights into the cosmological principle, the idea that the universe is homogeneous and isotropic on a large scale. If we can compile a sufficient catalog of black hole mergers across different regions and epochs, it might reveal patterns or anomalies that challenge our understanding of the cosmos. For example, do black hole merger rates vary significantly depending on their location in the universe? If so, what could this tell us about the conditions necessary for their formation? Additionally, black hole mergers might hold the key to unlocking one of the biggest mysteries in modern physics: the nature of quantum gravity. Black holes are unique laboratories where the classical theories of general relativity and the probabilistic laws of quantum mechanics clash. Understanding how spacetime behaves at the singularity, the heart of a black hole, requires a theory that unifies these two frameworks. While current observations of black hole mergers cannot directly probe the singularity, they do test the boundaries of general relativity under extreme conditions, offering tantalizing hints about where the theory might break down. One area where this becomes particularly interesting is the study of gravitational wave echoes. Some theoretical models predict that instead of a clean gravitational wave signal, the aftermath of a black hole merger might include faint echoes caused by quantum effects near the event horizon. Detecting such echoes would be groundbreaking, offering direct evidence of quantum modifications to black hole physics and potentially shedding light on phenomena like Hawking radiation or the information paradox. The information paradox itself is another thread woven into the narrative of black hole mergers. According to Stephen Hawking's calculations, black holes should slowly evaporate over time, emitting radiation that carries away their mass. But this raises a troubling question: what happens to the information about the matter and energy that fell into the black hole? Does it disappear forever, violating one of the fundamental principles of quantum mechanics, or is it somehow preserved? While the gravitational waves from mergers don't directly answer this paradox, they do provide a platform for exploring its implications. For example, some theories propose that information might be encoded in subtle features of the gravitational wave signal or preserved in a firewall at the event horizon. By studying black hole mergers in greater detail, we might uncover clues that help resolve this enigmatic puzzle, bridging the gap between the macroscopic world of gravity and the microscopic realm of quantum mechanics. Another compelling mystery tied to black hole mergers is the nature of dark matter. While gravitational wave observations primarily involve black holes formed from ordinary matter, there's growing speculation about the role dark matter might play in these events. Could some black hole mergers involve exotic objects made of dark matter, such as primordial black holes formed in the early universe? If so, their unique signatures could offer a glimpse into the elusive dark sector, revealing properties of dark matter that have remained hidden from traditional observational methods. Primordial black holes themselves are a fascinating subject. Unlike stellar mass black holes, which form from the collapse of massive stars, primordial black holes are thought to have formed from density fluctuations in the hot, dense environment of the early universe. If they exist, they could account for some or all of dark matter, and their mergers might produce gravitational wave signals distinguishable from those of ordinary black holes. Detecting such signals would revolutionize our understanding of both black holes and dark matter, providing a crucial link between cosmology and particle physics. The possibilities extend further when considering the interplay between black hole mergers and other cosmic phenomena. For example, could a black hole merger trigger the formation of new stars by compressing nearby gas clouds with its gravitational waves? Or might these waves interact with other spacetime distortions, such as those caused by cosmic strings or domain walls, to create observable effects? These speculative ideas, while still in their infancy, highlight the interconnectedness of the universe and the potential for black hole mergers to illuminate a wide range of astrophysical processes. Beyond the scientific implications, black hole mergers also inspire profound philosophical questions. They force us to confront the nature of existence itself, how such extreme objects can exist and interact in ways that defy our intuition. The idea that spacetime can ripple and stretch, that the universe itself is a dynamic entity, challenges our perception of reality. It reminds us that the cosmos operates on a scale and complexity far beyond human experience, offering a humbling perspective on our place within it. Furthermore, the study of black hole mergers underscores the power of human curiosity and collaboration. The discoveries made possible by gravitational wave astronomy are the result of decades of effort by an international community of scientists, engineers, and visionaries. They reflect the best of what humanity can achieve when we work together, driven by a shared desire to understand the universe. As we look to the future, the next generation of gravitational wave observatories promises to expand our horizons even further. Projects like the Einstein Telescope and the Cosmic Explorer aim to increase sensitivity by an order of magnitude, allowing us to detect black hole mergers at unprecedented distances and study their properties with unparalleled precision. Space-based missions like LISA will complement these efforts, opening up new frequency ranges and enabling the detection of supermassive black hole mergers and other exotic phenomena. The possibilities are as vast as the universe itself. Each new observation, Each faint signal detected amidst the cosmic noise brings us closer to answering fundamental questions about the nature of reality. Black hole mergers are not just cosmic collisions, they are gateways to understanding the deepest mysteries of existence. And as we continue to listen to the echoes of these titanic events, we find ourselves drawn ever deeper into the awe-inspiring story of the universe. The story of black hole mergers continues to unravel like a cosmic epic, with each discovery adding a new chapter to our understanding of the universe. As we refine our observational techniques and broaden our theoretical frameworks, we edge closer to answering some of the most perplexing questions about black holes, spacetime, and the very fabric of reality. Yet, for every answer we uncover, new questions arise, each one beckoning us further into the unknown. Take, for instance, the mysterious intermediate mass black holes, IMBHs. While stellar mass black holes and supermassive black holes are well documented, the existence of IMBHs remains speculative. These black holes are thought to bridge the gap between their smaller and larger counterparts, with masses ranging from hundreds to thousands of times that of the Sun. If IMBHs do exist, their mergers would produce gravitational waves with unique signatures, potentially detectable with current or future observatories. However, the elusive nature of IMBHs poses challenges. Their formation processes are poorly understood, and their environments may not lend themselves to frequent mergers. Some theories suggest that IMBHs could form in dense star clusters, where repeated collisions and accretions build up their mass. Others propose that they might be remnants of population 3 stars, the first generation of stars to form in the universe. Detecting an IMBH merger would not only confirm their existence but also shed light on these enigmatic processes, offering a window into the early stages of cosmic evolution. Another intriguing aspect of black hole mergers is their role in shaping the galaxies they inhabit. Black holes, particularly supermassive ones, are intimately connected to their host galaxies, influencing their formation and evolution through complex feedback mechanisms. When two galaxies merge, their central black holes are drawn together by gravitational forces, eventually forming a binary system. The inspiral and eventual merger of these black holes release enormous energy, potentially triggering star formation or altering the dynamics of the surrounding galaxy. These galactic-scale mergers also produce some of the loudest gravitational wave signals in the universe, detectable across vast cosmic distances. The study of such events provides valuable insights into galaxy formation and evolution, as well as the distribution and behavior of supermassive black holes. By mapping these mergers over time, astronomers can reconstruct the history of galaxy interactions and uncover patterns that reveal the large-scale structure of the universe. Adding to the complexity are the effects of spin and alignment in black hole mergers. Black holes are not static objects, they spin, and their spins can vary widely depending on their formation history. When two black holes merge, the alignment of their spins relative to their orbital planes significantly affects the dynamics of the merger, and the resulting gravitational wave signal. Misaligned spins can cause the orbital plane to precess, adding intricate modulations to the waveform. Understanding these spin dynamics is crucial for decoding the astrophysical origins of black hole binaries. For example, black holes formed in isolated binary star systems are expected to have aligned spins due to their shared evolutionary history. In contrast, those formed through dynamical interactions in dense star clusters or galactic nuclei are more likely to have random spin orientations. By analyzing the spin properties of merging black holes, scientists can infer the environments and processes that brought them together. The spin properties also have profound implications for the final remnant black hole formed after a merger. Depending on the masses and spins of the original black holes, the remnant can exhibit a phenomenon known as kick velocity. This occurs when asymmetries in the gravitational wave emission impart a recoil to the newly formed black hole, sometimes ejecting it from its host galaxy entirely. These runaway black holes, hurtling through intergalactic space, are fascinating objects in their own right and could provide new opportunities for observation and study. Beyond individual events, the cumulative effect of countless black hole mergers contributes to what is known as the gravitational wave background. This background consists of the faint, persistent hum of gravitational waves produced by numerous unresolved mergers throughout the universe. Detecting and characterizing this background is a major goal of gravitational wave astronomy, as it offers a comprehensive picture of the population and behavior of black holes across cosmic history. The gravitational wave background is particularly exciting because it encompasses events that are too distant or faint to detect individually. It represents the collective whisper of the cosmos, carrying information about the formation and evolution of black holes on a grand scale. Advanced detection techniques, combined with long-term observations, will be essential for teasing out this background signal from the noise, providing a deeper understanding of the universe's gravitational wave landscape. As we delve deeper into the study of black hole mergers, we also confront the possibility of entirely new physics. The extreme conditions surrounding these events, intense gravitational fields, high velocities, and enormous energy scales, push the limits of our current theories. They provide an unparalleled opportunity to test general relativity in regimes where deviations from its predictions might occur. Any observed discrepancies could point to new phenomena or even hint at the existence of additional dimensions or fundamental forces. Moreover, black hole mergers might reveal connections between seemingly disparate areas of physics. For example, some theories suggest that black holes could be linked to holography, a concept from string theory that describes the universe as a two-dimensional surface encoding three-dimensional information. If this holographic principle applies to black holes, their mergers could produce observable effects that offer clues about the nature of spacetime and information. The implications extend even to cosmology. Black hole mergers provide a unique method for measuring the expansion rate of the universe, known as the Hubble constant. By combining gravitational wave observations with electromagnetic counterparts, if present, astronomers can directly calculate distances and redshifts, offering an independent means of resolving the current tension between different measurements of the Hubble constant. This dual capability of black hole mergers, probing both astrophysical and cosmological phenomena, highlights their importance as a unifying theme in modern science. They are not isolated occurrences but integral components of the cosmic tapestry, interconnected with everything from the life cycle of stars to the large-scale structure of the universe. Ultimately, the study of black hole mergers is a testament to human ingenuity and the boundless curiosity that drives us to explore the unknown. Each gravitational wave detected, each signal decoded, brings us one step closer to understanding the cosmos in its entirety. And yet, the mysteries that remain are as vast and profound as the universe itself, ensuring that the journey of discovery will continue for generations to come. The journey into the mysteries of black hole mergers takes us deeper into the intersections of science and the vast unknown. As we continue to explore these titanic collisions, we must also consider the role of advanced technology in enabling such discoveries. Without the cutting-edge capabilities of instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, Virgo, and CAGRA, our understanding of these events would remain confined to theoretical speculation. Gravitational wave detectors operate with a sensitivity that borders on the surreal. They are designed to measure distortions in spacetime on scales smaller than the diameter of a proton, an achievement that speaks to the ingenuity and precision of modern engineering. These detectors function by using laser beams to measure minute changes in the lengths of perpendicular arms caused by passing gravitational waves. When a black hole merger occurs, the ripples it sends across spacetime alter these distances ever so slightly, creating a signal that scientists can analyze. The ability to detect these signals represents a seismic shift in astronomy. Before the advent of gravitational wave observatories, black holes were studied primarily through their interactions with visible matter, such as stars and gas. Observing these interactions often required assumptions about the black hole's environments and behaviors. Gravitational wave astronomy, however, offers a direct method of detecting black holes and understanding their properties without relying on indirect observations. One remarkable aspect of this new observational era is how gravitational waves provide information that is complementary to electromagnetic signals. While traditional telescopes observe light in various forms, from visible to radio waves, gravitational waves offer an entirely different kind of insight. They carry information about mass, velocity, and the dynamics of objects involved in extreme events like black hole mergers. This dual approach, combining electromagnetic and gravitational wave data, is known as multimessenger astronomy. Multimessenger astronomy has already yielded groundbreaking results. For instance, when LIGO and Virgo detected a neutron star merger in 2017, astronomers around the world pointed their telescopes at the same region of the sky to capture its electromagnetic counterpart. This event, known as GW170817, provided unprecedented insights into phenomena like kilonovae and the origins of heavy elements. While black hole mergers often lack electromagnetic counterparts due to their isolated nature, similar techniques are being employed to maximize the scientific returns of each detection. As our observational capabilities improve, we are beginning to probe black hole mergers in increasingly diverse environments. For instance, some mergers occur in dense stellar nurseries, where stars are born and die in rapid succession. These regions, known as globular clusters, are rich with interactions that can lead to the formation of binary black holes. Other mergers might take place in the chaotic cores of galaxies, where supermassive black holes dominate the gravitational landscape. One particularly fascinating environment for black hole mergers is active galactic nuclei, AGN. These are regions around supermassive black holes where enormous amounts of gas and dust are accreted, producing intense radiation. The extreme gravitational and electromagnetic forces in AGN can trap smaller black holes, forcing them into close orbits that eventually lead to mergers. Studying such events could reveal how black holes interact with their surroundings under extreme conditions. The search for black hole mergers also extends beyond our galaxy. While most of the gravitational waves detected so far have originated in relatively nearby regions of the universe, on cosmic scales, researchers are pushing the boundaries to detect mergers from earlier epochs of cosmic history. These events, occurring billions of years ago, hold clues about the formation and evolution of the first black holes and their role in shaping the young universe. To detect these distant events, scientists are developing next-generation gravitational wave observatories, such as the Einstein Telescope and the Laser Interferometer Space Antenna, LISA. These instruments will operate at lower frequencies, allowing them to observe signals from more massive black holes and over longer timescales. LISA, in particular, is a space-based observatory that will consist of 3 satellites arranged in a triangular formation, separated by millions of kilometers. Its unprecedented sensitivity will enable it to detect mergers involving supermassive black holes at the heart of distant galaxies. The potential discoveries from such observatories are staggering. They could uncover the origins of the supermassive black holes that reside in nearly every galaxy, including our Milky Way. These behemoths, with masses millions or billions of times that of the Sun, are thought to have grown through a combination of mergers and accretion. However, their rapid growth in the early universe remains one of the greatest puzzles in astrophysics. Some theories suggest that supermassive black holes formed from the collapse of massive clouds of gas in the early universe, bypassing the need for a stellar precursor. Others propose that they began as smaller black holes, which then grew through successive mergers. Detecting the gravitational waves from these early mergers would provide direct evidence to support or refute these hypotheses, offering a glimpse into an era of cosmic history that is otherwise inaccessible. As we consider the profound implications of black hole mergers, it is impossible to ignore their connection to some of the most fundamental questions in physics. Black holes are not merely astrophysical objects, they are also laboratories for testing the limits of our understanding of gravity, spacetime, and quantum mechanics. The extreme conditions surrounding mergers, where gravitational fields are at their strongest and spacetime is most warped, offer a unique opportunity to probe these frontiers. One tantalizing possibility is that black hole mergers could reveal deviations from general relativity, the theory proposed by Albert Einstein over a century ago. While general relativity has been remarkably successful in describing the behavior of gravity on large scales, it is known to be incomplete, particularly when it comes to reconciling gravity with quantum mechanics. Any observed discrepancies in the gravitational wave signals from black hole mergers could hint at new physics, such as the existence of quantum gravity or extra dimensions. Some physicists also speculate that black hole mergers could be linked to the mysterious phenomenon of dark matter. Dark matter, which constitutes about 27% of the universe, is invisible and interacts primarily through gravity. If dark matter particles are involved in the dynamics of black hole binaries or their mergers, their presence might leave subtle imprints on the gravitational wave signals. Detecting such imprints would revolutionize our understanding of the universe's hidden components. The study of black hole mergers is a dynamic and rapidly evolving field, driven by both technological advancements and the insatiable curiosity of scientists. Each detection adds a new piece to the puzzle, revealing not only the secrets of black holes but also the broader workings of the cosmos. Yet, despite the progress made, the mysteries that remain are as vast and enigmatic as the universe itself. The ongoing exploration of black hole mergers is a testament to humanity's relentless drive to understand the cosmos. These events, which unfold on scales that boggle the imagination, are windows into the most extreme phenomena in nature. But while our current understanding has deepened, it has also raised profound questions that challenge our grasp of reality. One of the most intriguing aspects of black hole mergers lies in their role in shaping the universe's structure. Black holes are not just endpoints of massive stars, they are cosmic architects. When they merge, the resulting black hole often receives a kick due to asymmetries in the gravitational waves emitted during the collision. This recoil can propel the merged black hole across its host galaxy at incredible speeds, sometimes ejecting it entirely. These rogue black holes could roam the intergalactic void, creating gravitational distortions in their wake. Understanding how often this occurs helps scientists model the distribution of black holes and their impact on galaxy evolution. Another fascinating element of black hole mergers is their potential link to cosmic voids, vast, empty regions of space that contain very few galaxies. These voids are a striking feature of the large-scale structure of the universe, but their origins remain mysterious. Some theories suggest that black hole mergers, particularly in the early universe, may have contributed to the formation or expansion of these voids. If true, the gravitational wave signals we detect today could carry echoes of these primordial events, offering a direct glimpse into the universe's earliest moments. The study of black hole mergers also intersects with the enigma of black hole spins. When two black holes merge, the spin of the resulting black hole depends on the spins and alignments of the original pair. By analyzing gravitational wave signals, scientists can infer these properties and gain insights into the formation mechanisms of binary black holes. For example, if the spins are randomly aligned, it suggests that the black holes formed in a dense, chaotic environment like a globular cluster. If the spins are aligned, it points to a more serene origin, such as the collapse of a binary star system. These clues help unravel the life stories of black holes and their journeys across cosmic time. Yet, there is another layer of complexity, the nature of the singularity. At the heart of every black hole lies a singularity, a point where density becomes infinite, and our current laws of physics break down. When two black holes merge, their singularities must somehow combine, but the exact process remains a mystery. Does the singularity of the new black hole form instantly, or does it undergo a transient phase? And what does this say about the fabric of spacetime itself? These questions push the boundaries of theoretical physics, requiring models that go beyond general relativity. One possibility is that black hole mergers could provide evidence for phenomena predicted by quantum gravity. For instance, some theories suggest that singularities might not exist as true infinities but instead represent regions where quantum effects dominate. These quantum black holes might exhibit properties that subtly alter the gravitational wave signals emitted during a merger. Detecting such deviations would be a groundbreaking achievement, offering the first glimpses of a unified theory of physics. Adding to the intrigue is the idea that black hole mergers might create exotic remnants. While most mergers produce a larger black hole, some theories propose the possibility of naked singularities, or other exotic objects that defy conventional classification. These remnants could challenge our understanding of cosmic censorship, a principle that suggests singularities are always hidden behind event horizons. Observing such anomalies would force a reevaluation of some of the most fundamental assumptions in astrophysics. The role of black hole mergers in the context of dark energy is another area ripe for exploration. Dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the greatest puzzles in cosmology. Some researchers speculate that black hole mergers, particularly those involving supermassive black holes, could influence the dynamics of dark energy on cosmic scales. This connection, though highly speculative, underscores the interconnectedness of seemingly disparate phenomena in the universe. As we push forward, the search for black hole mergers is expanding into new observational frontiers. Future gravitational wave detectors, such as the Einstein telescope and LISA, will operate with unparalleled sensitivity, allowing us to probe mergers involving black holes of all sizes and in all environments. These observatories will open a window into the mergers of supermassive black holes, which occur at the centers of galaxies and shape their evolution. They will also enable the detection of primordial black holes, hypothetical objects formed in the early universe that could provide clues about the origins of cosmic structure and the nature of dark matter. The interplay between observation and theory is key to unraveling the mysteries of black hole mergers. Each new detection challenges existing models and inspires novel hypotheses. For instance, recent observations of mergers involving unusually massive black holes have prompted questions about their formation pathways. Are these black holes the result of repeated mergers in dense stellar environments, or do they represent a distinct population formed through unknown processes? Answering these questions requires a synthesis of data from gravitational wave astronomy, electromagnetic observations, and theoretical simulations. At the same time, black hole mergers invite philosophical reflection on the nature of the universe and our place within it. These events, which unfold over billions of light years, are a stark reminder of the vastness and complexity of the cosmos. Yet they also highlight the remarkable capacity of human ingenuity to understand phenomena that transcend ordinary experience. By detecting and interpreting the faint whispers of gravitational waves, we are reaching across spacetime to uncover the secrets of cosmic giants. The study of black hole mergers is not merely an academic pursuit, it is a testament to the power of curiosity and the human spirit. These collisions, which began as abstract mathematical predictions, are now tangible realities that we can observe and analyze. Each discovery brings us closer to answering fundamental questions about the universe while revealing new layers of complexity and wonder. In this sense, black hole mergers serve as a metaphor for the scientific endeavor itself. Just as these cosmic collisions create ripples that travel across spacetime, our exploration of the universe generates ripples of knowledge that extend into the future. With each step forward, we uncover deeper truths about the cosmos and our connection to it, affirming the boundless potential of human inquiry. These cosmic collisions also provide insights into the ultimate fate of black holes and the broader universe. As black holes merge and grow larger over time, they contribute to the evolution of the universe's overall structure. One fascinating question is whether such mergers could lead to the eventual dominance of supermassive black holes in the far future. In a universe where stars burn out and galaxies fade, black holes might represent one of the final stages of cosmic evolution, a concept that adds a layer of existential curiosity to their study. Another intriguing concept tied to black hole mergers is the idea of gravitational wave memory. This phenomenon refers to a permanent distortion of spacetime caused by the passage of gravitational waves. Imagine spacetime as a stretched fabric. When a black hole merger sends out ripples, these waves leave a lasting imprint, subtly altering the relative positions of objects in their path. Detecting this memory effect could provide additional confirmation of the predictions of general relativity and offer yet another way to study these extraordinary events. As we look further into the role of black hole mergers, one of the most exciting developments is the potential to use these events as standard sirens for measuring the expansion of the universe. Much like how supernovae are used as standard candles in astronomy, the gravitational wave signals from black hole mergers can provide a direct measure of distance. By comparing the detected signals to their theoretical models, scientists can calculate how far away the merger occurred. This method allows researchers to map the rate at which the universe is expanding and refine measurements of the Hubble constant, a value that has been notoriously difficult to pin down with traditional techniques. The more precise our understanding of the Hubble constant becomes, the closer we get to resolving one of cosmology's greatest debates: the apparent discrepancy between measurements made using the early universe, via the cosmic microwave background, and the modern universe, via supernovae and other observations. Black hole mergers offer an independent method to bridge this gap, potentially uncovering new physics that explains why these measurements differ. One of the most significant aspects of black hole mergers is their ability to probe the fundamental nature of gravity itself. General relativity has been an incredibly successful theory, but it is not the final word on how gravity operates, particularly under extreme conditions. The intense gravitational environments created by black hole mergers provide a unique testing ground for alternative theories of gravity. For example, some models suggest that gravitational waves might travel at slightly different speeds or exhibit deviations from the waveforms predicted by general relativity. Detecting such anomalies would revolutionize our understanding of gravity and point the way toward a more complete theory. Moreover, black hole mergers are also linked to the search for exotic phenomena, such as cosmic strings. These hypothetical defects in spacetime, thought to be remnants of the early universe, could produce unique signatures in gravitational wave observations. If a black hole merger occurred near a cosmic string, the resulting waves might carry distinct patterns that revealed the string's presence. Detecting such signals would not only confirm the existence of cosmic strings but also provide a glimpse into the universe's earliest moments, when spacetime itself was still forming. The study of black hole mergers also intersects with the enigma of time itself. Black holes, by their very nature, warp spacetime to an extreme degree. Near a black hole's event horizon, time slows dramatically compared to regions far away. When two black holes merge, this warping becomes even more pronounced, creating conditions where time and space blur together in ways that defy intuition. Understanding these effects could shed light on the nature of time and its relationship to the universe's underlying fabric. On a practical level, black hole mergers highlight the interconnectedness of modern astronomy. These events often produce not only gravitational waves but also electromagnetic signals, such as bursts of light, gamma rays, or even neutrinos. Coordinating observations across multiple types of detectors, gravitational wave observatories, telescopes, and particle detectors, creates a more complete picture of these events. This multimessenger approach is transforming how we study the universe, enabling discoveries that would be impossible using a single type of observation. As we refine our ability to detect black hole mergers, we are also pushing the boundaries of technology. Gravitational wave observatories like LIGO and Virgo rely on instruments of astonishing precision, capable of detecting changes in distance smaller than the width of a proton. Future upgrades and new observatories, such as the space-based LISA, will take this sensitivity even further, opening up new possibilities for studying black holes and other cosmic phenomena. The implications of black hole mergers extend beyond astrophysics and into the realm of philosophy. These events force us to confront the limits of human understanding and the sheer scale of the universe. They remind us that we are part of a vast, interconnected cosmos, where even the most violent and extreme phenomena are governed by underlying principles that we are only beginning to uncover. This sense of wonder and curiosity is at the heart of scientific exploration, driving us to ask deeper questions about the universe and our place within it. As we continue to study black hole mergers, we are not just learning about distant collisions, we are also learning about ourselves. These events, which unfold over billions of years and across incomprehensible distances, highlight the power of human ingenuity and the potential of collaboration. By working together to decode the signals of the universe, we are uncovering truths that transcend time. The story of black hole mergers is far from over. Each new detection adds a piece to the puzzle, revealing a universe that is more dynamic, complex, and awe-inspiring than we ever imagined. With every gravitational wave that reaches Earth, we are reminded of the interconnectedness of all things, a reminder that even in the vastness of space, the ripples of distant collisions can touch us here, grounding us in a shared quest for knowledge and understanding. As we continue to push the limits of our understanding of black hole mergers, we delve deeper into the fascinating mechanics of these cosmic giants. One of the most awe-inspiring aspects of black hole mergers is the way they challenge our perception of what is possible in the universe. These colossal objects, often hundreds or even thousands of times the mass of our Sun, collide with such intensity that they release energy equivalent to several solar masses in the form of gravitational waves. This immense power is incomprehensible to our everyday experience, but it is these very phenomena that allow us to test the laws of physics in ways that were once thought impossible. The concept of gravitational wave astronomy has emerged as one of the most exciting frontiers in modern physics. Black hole mergers have allowed us to create a new kind of map of the universe, one based not on light, but on the ripples that propagate through spacetime itself. Gravitational waves carry with them not just information about the black holes involved, but about the very fabric of space and time. This method of observation offers a new perspective on the universe, one that is completely different from traditional astronomy. Understanding the origins of these gravitational waves is not just an academic pursuit. Every black hole merger offers us a glimpse into some of the most extreme conditions in the universe. When two black holes spiral inward toward each other, they create a gravitational dance that stretches and warps spacetime in ways that are not fully understood. The merger itself marks the release of a tremendous burst of energy, a phenomenon that defies even our most advanced mathematical models. By studying these events, we hope to uncover new principles that govern the interactions of such massive objects. One of the most profound questions that arise from black hole mergers concerns the nature of the event horizon, the boundary around a black hole beyond which nothing, not even light, can escape. When two black holes merge, the resulting object forms a new black hole with its own event horizon. The complex behavior of this boundary, particularly in the context of mergers, raises important questions about the ultimate fate of matter and information in the universe. Do the laws of physics break down at the event horizon, or is there a deeper understanding that we have yet to uncover? This brings us to the paradox of black holes, the information paradox. In theory, when matter falls into a black hole, it is lost forever. However, recent studies suggest that information may not be completely destroyed, but rather transformed or encoded in some way that we do not yet understand. Some have proposed that gravitational waves could carry the missing information about the matter that falls into black holes, providing us with a way to resolve this paradox. The detection of gravitational waves from black hole mergers could play a crucial role in unraveling this mystery, offering insights into the fundamental nature of space, time, and the very fabric of the universe. In addition to the questions surrounding the physics of black holes themselves, black hole mergers also give us valuable clues about the formation and evolution of these enigmatic objects. We now know that black holes are not solitary objects, but often exist in pairs or even groups. The mergers we observe today are the result of a long, complex history that involves the interaction of black holes with their surroundings. Over time, black holes can acquire companions, either through the gravitational pull of nearby objects or through the collapse of massive stars. As these black holes orbit one another, they lose energy and spiral closer together, eventually merging in a cataclysmic event. The rate at which these mergers occur and the specific conditions that lead to them are areas of active research. We know that black holes are often found in regions of space with high stellar densities, such as the centers of galaxies or dense star clusters. It is in these environments that black holes are most likely to encounter each other and merge. Understanding these environments is crucial for predicting how often black hole mergers will occur and how the properties of the merging black holes will vary. For example, the mass, spin, and orientation of the black holes involved in a merger all influence the resulting gravitational waves and can provide us with important clues about their origins. In recent years, astronomers have begun to explore the possibility that some black hole mergers may be the result of interactions between black holes and other exotic objects, such as neutron stars. Neutron stars, the remnants of massive stars that have exploded in supernovae, are incredibly dense objects that can also produce gravitational waves when they collide. The detection of a black hole neutron star merger would be a groundbreaking discovery, as it would provide us with an unprecedented opportunity to study the behavior of matter under extreme conditions. While no such merger has been observed yet, the possibility remains an exciting prospect for future gravitational wave observations. Looking to the future, the continued detection of black hole mergers holds the promise of even more groundbreaking discoveries. As gravitational wave observatories become more sensitive and new instruments are developed, we will be able to observe increasingly distant and faint mergers, expanding our knowledge of these events and their role in the universe. The next generation of gravitational wave detectors, such as the Laser Interferometer Space Antenna, LISA, will allow us to observe mergers that occur much farther away than is currently possible, opening up a whole new realm of possibilities for black hole research. Furthermore, as we refine our understanding of black hole mergers, we may also learn more about the fundamental structure of the universe itself. The ripples created by these mergers provide a unique opportunity to probe the fabric of spacetime on the smallest scales. By studying the details of the gravitational waves produced by black hole mergers, we can test the predictions of general relativity and explore the possibility of new physics beyond our current understanding. One particularly exciting area of research is the potential connection between black hole mergers and the nature of dark matter. Dark matter is a mysterious substance that makes up a significant portion of the universe's mass, yet it has eluded direct detection. Some scientists have hypothesized that black hole mergers could provide indirect evidence for the existence of dark matter. By analyzing the gravitational waves from these mergers, we may be able to detect subtle anomalies that could reveal the presence of dark matter or other exotic forms of matter. While this idea is still speculative, it represents one of the many ways in which black hole mergers could lead to new discoveries about the universe's most fundamental components. Ultimately, black hole mergers are more than just spectacular cosmic events. They are keys to unlocking some of the most profound mysteries of the universe. By studying these collisions, we are not only learning about black holes themselves but also gaining insights into the nature of space, time, and the fundamental forces that govern the cosmos. As our understanding of these mergers deepens, we may find ourselves on the cusp of discovering entirely new realms of physics, revealing a universe far more complex and extraordinary than we ever imagined. Each new detection of a black hole merger is a reminder of the vastness of the universe and the endless possibilities for discovery. These cosmic events, which take place billions of light years away, have the power to transform our understanding of the universe and our place within it. In the process, they remind us that the pursuit of knowledge is not just about answering questions but about asking even deeper ones, questions that challenge our understanding of reality itself and push the boundaries of human curiosity. As we continue to investigate black hole mergers, it becomes increasingly apparent that these cosmic events could reshape how we perceive the universe. These mergers are not just phenomena occurring in the distant corners of space. They represent the ultimate test of our current theories of gravity, spacetime, and the very laws of physics that govern the cosmos. Every detection, every piece of data, brings us closer to unveiling secrets that have been hidden for eons. One of the key insights that black hole mergers offer us is a better understanding of the so-called final state of massive stars. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, often leaving behind a remnant that can collapse into a black hole. However, before this final stage, the star's life is governed by complex processes that eventually lead to a supernova. These supernovae, in turn, leave behind black holes that can then interact and merge with others over time. The astrophysical journey of black hole mergers starts long before the event itself. The process begins when massive stars form, burn their fuel, and end their lives in dramatic explosions. The remnants of these stars can either form neutron stars or black holes, depending on the initial mass of the star. In some cases, a binary system may form, where two black holes orbit each other in a gravitational dance. Over millions to billions of years, the two black holes spiral inward due to the loss of energy from the emission of gravitational waves, until they eventually collide in a final, cataclysmic merger. The merger of black holes is a truly unique event in the universe. The energy released during these mergers is so immense that it can ripple through spacetime itself. This ripple, known as gravitational waves, is the key to detecting these otherwise invisible phenomena. In fact, it was only in 2015 that the first direct detection of gravitational waves, caused by the merger of two black holes, confirmed a century-old prediction made by Albert Einstein. Since that groundbreaking discovery, gravitational wave astronomy has blossomed, allowing us to detect more mergers and probe the universe in ways never before thought possible. With every black hole merger detected, we gain not only more data about these mysterious objects, but also a glimpse into the nature of spacetime itself. Gravitational waves offer us an entirely new way of observing the universe. Unlike electromagnetic radiation, which can be blocked or absorbed by interstellar dust or other cosmic obstacles, gravitational waves travel through space virtually unhindered. This makes them an invaluable tool for studying the most distant and most extreme phenomena in the cosmos. The importance of these observations extends beyond black hole mergers. By studying gravitational waves from these events, scientists are learning more about the properties of spacetime, the structure of black holes, and even the nature of fundamental forces. For example, the data from the merger of two black holes can reveal crucial details about their masses, spins, and the way they interact before and after the collision. This, in turn, provides us with more insight into how black holes form, evolve, and interact with their environments. But black hole mergers also prompt us to confront the very nature of reality. When two black holes merge, they form a new, larger black hole, but this process doesn't come without its mysteries. The event horizon, the boundary beyond which nothing, not even light, can escape, of the newly formed black hole presents a puzzle. The merger of two black holes causes the formation of a new event horizon, but the behavior of the material and energy at that boundary is still a topic of intense research. Understanding how matter behaves at the event horizon, and whether information can escape from it, is one of the most profound challenges in modern physics. One of the most compelling ideas that arises from studying black hole mergers is the nature of information. In classical physics, the idea that information can be destroyed was unacceptable. However, in the case of black holes, it seemed as if information about the matter that falls into them could be lost forever. This is known as the black hole information paradox. When black holes merge, they combine the mass, charge, and angular momentum of both black holes, but do they retain information about the original objects? Theories like the holographic principle suggest that the information about the matter that falls into a black hole might not be lost but rather encoded on the event horizon itself. If this is true, black hole mergers could provide a unique opportunity to test this idea. The detection of gravitational waves from black hole mergers could potentially offer us clues about how information is stored or preserved in these enigmatic objects, and whether our current understanding of quantum mechanics and gravity is in need of revision. The study of black hole mergers also raises questions about the very nature of dark energy, a mysterious force that is driving the accelerated expansion of the universe. While dark energy and black holes might seem unrelated, the gravitational waves produced by black hole mergers could reveal subtle clues about the larger cosmological landscape. Some theorists speculate that the way black holes interact with spacetime could offer indirect evidence of dark energy's properties. This idea, though speculative, highlights the interconnectedness of different forces and phenomena in the universe. If black hole mergers can help us understand the role of dark energy, it would be a groundbreaking discovery that could rewrite the fundamental laws of cosmology. Looking even further into the future, black hole mergers may help us unlock even more profound mysteries of the universe, including the nature of the multiverse. Some theories suggest that black holes could be gateways to parallel universes or different regions of spacetime. If black holes are connected to other realms, then their mergers may not just signify the end of one black hole but the creation of a new, vast region of the cosmos. While these ideas are still highly speculative, the study of black hole mergers could be the key to understanding the true scale of the universe and its possible infinite nature. On a practical level, the detection of black hole mergers has far-reaching implications for our technological advancements. The tools and methods used to detect gravitational waves are incredibly advanced and continue to evolve. The technology that has allowed us to observe these cosmic events has led to innovations in fields like precision measurement, laser technology, and data analysis. These advancements are not just beneficial for astrophysics. They have practical applications in other areas of science and technology, including medicine, engineering, and communications. In the coming decades, the development of more advanced gravitational wave detectors will undoubtedly lead to even more groundbreaking discoveries. The Laser Interferometer Space Antenna, LISA, which is set to launch in the 2030s, will provide an unprecedented level of sensitivity and allow us to observe black hole mergers that are farther away and much fainter than what is possible today. With its ability to detect lower frequency gravitational waves, LISA will enable us to explore a new range of black hole mergers and other astrophysical events, dramatically expanding our understanding of the universe. At the same time, the advancement of ground-based detectors, such as LIGO and Virgo, will continue to provide valuable data on black hole mergers and other cosmic events. The future of gravitational wave astronomy is bright, and as we refine our observational techniques, we will likely uncover even more surprising and awe-inspiring phenomena that we can barely imagine today. Ultimately, black hole mergers represent one of the most profound mysteries of the cosmos. They challenge our understanding of space, time, and the very nature of the universe itself. Through the study of these cosmic collisions, we are not just learning about black holes, we are learning about the fundamental forces that shape the universe, and in doing so, we are beginning to unlock the deepest secrets of existence. Every detection of a black hole merger is a step closer to unraveling the mysteries of the cosmos. As our technology and understanding evolve, we will continue to witness the merging of these cosmic giants, offering us glimpses into the most extreme and enigmatic events in the universe. The quest for knowledge is far from over, and as we push the boundaries of what we can observe and understand, we inch closer to uncovering the true nature of black holes, spacetime, and the universe itself. As we continue to explore the complexities of black hole mergers, the field of gravitational wave astronomy is becoming increasingly refined. Each new detection not only adds to our understanding of black hole dynamics but also provides us with an opportunity to test and refine the laws of physics. The current and future detectors, like LIGO, Virgo, and LISA, are poised to reveal even more startling insights into the most violent and energetic events in the universe. These detectors are not only looking at the obvious, massive black holes merging, but are also observing a whole range of astrophysical phenomena that may have been previously invisible to us. One of the most exciting aspects of gravitational wave astronomy is the potential to observe events that would otherwise be impossible to detect through traditional methods. For example, the collision of two black holes generates gravitational waves, a phenomenon that leaves no electromagnetic radiation behind. If we relied solely on traditional optical telescopes, we would be completely blind to these events. But thanks to the detection of gravitational waves, we are able to observe the signals created by these mergers and, in some cases, even trace them back to their origins. This opens up an entirely new way of observing the universe that goes beyond the limitations of light, allowing us to probe the most distant, hidden regions of space. This newfound ability to observe black hole mergers also raises some tantalizing possibilities for future discoveries. For instance, while we currently detect only the largest and most energetic black hole mergers, as our detectors become more sensitive, we may begin to detect smaller, more frequent events. These events could provide us with even greater insights into the populations of black holes that inhabit the universe. By detecting these mergers, we might learn more about how black holes form in the first place, how they interact with their environments, and how they evolve over time. Additionally, black hole mergers may also offer us the opportunity to study the nature of the fundamental forces in the universe in a way that was previously impossible. One of the most exciting prospects is the potential to use gravitational wave observations to test Einstein's theory of general relativity in extreme conditions. While general relativity has been confirmed in a wide range of situations, the incredibly strong gravitational fields created by black hole mergers present a unique environment where even the smallest deviations from general relativity might be detectable. By carefully analyzing the gravitational waves from black hole mergers, scientists can search for subtle clues that might indicate the need for new physics. In fact, some theorists suggest that black hole mergers could reveal new aspects of quantum mechanics. For decades, physicists have struggled with reconciling general relativity, which describes the large-scale structure of spacetime, with quantum mechanics, which governs the behavior of the smallest particles. These two pillars of modern physics have been remarkably successful in their respective domains, but they have yet to be united into a single theory. The merger of black holes, with their extreme gravitational fields and the presence of quantum effects near the event horizon, may provide a natural laboratory for testing the limits of our understanding of both quantum mechanics and gravity. As we continue to observe and analyze these black hole mergers, we must also consider their role in the broader cosmic landscape. Black hole mergers are not just isolated events, they are connected to the larger evolution of galaxies and the universe itself. The merging of black holes could have profound implications for the formation and growth of galaxies. In fact, some scientists speculate that the growth of supermassive black holes at the centers of galaxies could be linked to the mergers of smaller black holes. The gravitational waves produced by these mergers might provide us with a unique way of studying the history of galaxy formation and the role black holes play in shaping the structure of the cosmos. Moreover, black hole mergers may also be connected to other enigmatic phenomena, such as the mysterious dark matter that makes up a large portion of the universe's mass. While dark matter has yet to be directly detected, it is believed to exist because of its gravitational effects on visible matter. Some theories suggest that black hole mergers could be influenced by or even contribute to the formation of dark matter. By studying the gravitational waves from these mergers, scientists may be able to learn more about the nature of dark matter and how it interacts with the rest of the universe. If dark matter is indeed linked to the behavior of black holes, it could open up a whole new avenue of research that could fundamentally alter our understanding of the universe's composition. On a more philosophical note, the study of black hole mergers forces us to confront some of the deepest questions about the nature of reality itself. What happens to matter and energy when it crosses the event horizon of a black hole? Does it simply vanish, or is there some deeper process at work? Is there a way to observe or even interact with the information that is thought to be lost inside a black hole? These questions remain at the forefront of scientific inquiry and have far-reaching implications for our understanding of the universe. In the future, as technology continues to advance, we will likely see an explosion of new data and discoveries related to black hole mergers. With each new merger we detect, we will gain more insights into the nature of black holes, the properties of spacetime, and the fundamental forces that govern the cosmos. But more than that, black hole mergers remind us of the vastness and mystery of the universe, and the potential for discovery is limitless. Just as we are beginning to understand these cosmic giants, we are only scratching the surface of the many secrets they hold. There is much more to be learned about black hole mergers, and the journey is far from over. Each new observation, each new wave of data, brings us closer to answering some of the biggest questions in science. How do black holes form? What happens to matter at the event horizon? Can we reconcile quantum mechanics and general relativity? What role do black hole mergers play in the evolution of galaxies and the universe? These questions may seem vast and unknowable, but with each breakthrough, we are moving closer to understanding the cosmic dance of black hole mergers and the fundamental nature of the universe. In the coming decades, as our understanding of black hole mergers deepens, we may find that the answers to these questions are even more surprising and mind-bending than we could have imagined. The future of gravitational wave astronomy is incredibly exciting, and the study of black hole mergers will continue to be one of the most important areas of research in astrophysics. The universe is full of mysteries, and black hole mergers are just one piece of the cosmic puzzle that we are only beginning to understand. As we continue our exploration of these enigmatic events, we may also discover that the universe itself is more interconnected and complex than we ever thought possible. Each black hole merger, each burst of gravitational waves, could be a key that unlocks even deeper mysteries, leading us to new insights about the nature of space, time, and the cosmos itself. As we delve deeper into the realm of black hole mergers and gravitational waves, it's essential to recognize the broader implications of these phenomena. The detection of gravitational waves has opened up an entirely new window into the universe, one that was previously invisible to us. Unlike light, gravitational waves can travel through space without being scattered or absorbed by matter. This makes them a powerful tool for observing events that would otherwise be hidden, such as the collision of two black holes. But what does this mean for the future of astronomy and our understanding of the cosmos? The first detection of gravitational waves in 2015 marked a major milestone in our understanding of the universe. It confirmed the existence of ripples in spacetime, as predicted by Albert Einstein a century earlier. The waves that were detected came from the merger of two black holes, and the event provided scientists with a wealth of data. The merger of these two black holes released an enormous amount of energy, equivalent to the mass of several suns, in the form of gravitational waves. This discovery opened the floodgates to a new era of observational astronomy, where gravitational wave detectors are becoming increasingly sensitive and able to detect more subtle events. Since that groundbreaking detection, there have been numerous other black hole mergers observed, each one providing new insights into the behavior of these enigmatic objects. With each detection, scientists are refining their models of black hole physics, exploring the behavior of matter in extreme gravitational fields, and testing the limits of our understanding of the laws of physics. But the story doesn't stop with just the discovery of these mergers. Each observation brings new questions to light, propelling us to explore deeper mysteries of the universe. One of the fascinating aspects of black hole mergers is the information they reveal about the properties of the black holes involved. When two black holes collide, they form a new, larger black hole. The process generates gravitational waves, but it also provides clues about the properties of the original black holes, such as their masses, spins, and the nature of their interactions. By studying the signals produced by these mergers, scientists can learn more about how black holes form and evolve over time. The properties of the newly formed black hole can also provide valuable information about the dynamics of the merger process itself. For example, one of the key parameters that scientists look at when analyzing black hole mergers is the mass of the resulting black hole. In some cases, the mass of the new black hole is exactly what we would expect based on the masses of the original black holes. However, in other cases, there is a discrepancy between the expected and actual mass. This could be due to the emission of gravitational waves during the merger process, which carries away some of the energy that would otherwise contribute to the mass of the resulting black hole. These discrepancies provide an opportunity to test our understanding of black hole dynamics, and may hint at new physics that we have yet to fully grasp. Another intriguing aspect of black hole mergers is the role that the spins of the black holes play in the outcome of the merger. Black holes are not stationary. They can rotate at incredibly high speeds. The spin of a black hole influences the shape of the gravitational waves produced during a merger and can affect the final mass and spin of the resulting black hole. By carefully analyzing the spin properties of black holes in merger events, scientists can gain insights into how these objects form and evolve, as well as the processes that govern their interactions. In particular, the alignment or misalignment of the spins of the two black holes can have a significant impact on the dynamics of the merger. As we continue to observe more black hole mergers, scientists are also exploring the possibility of detecting mergers involving more exotic objects, such as neutron stars. While black hole mergers are the most common events detected so far, neutron star mergers are also a source of intense interest. Neutron stars are the remnants of massive stars that have gone supernova, and they are incredibly dense objects. When two neutron stars merge, they can produce both gravitational waves and electromagnetic radiation, such as gamma-ray bursts. The combination of these two signals makes neutron star mergers particularly intriguing, as they offer the opportunity to study both the gravitational and electromagnetic aspects of these events. One of the most significant aspects of neutron star mergers is the potential for heavy element production. When two neutron stars collide, the resulting explosion can create heavy elements such as gold and platinum. This process, known as nucleosynthesis, is thought to be responsible for the creation of many of the heavy elements in the universe. By studying the gravitational waves produced by these mergers, scientists can learn more about the conditions under which these elements are formed, as well as the role that neutron-star mergers play in the evolution of the universe's chemical composition. While black hole mergers and neutron-star mergers are fascinating in their own right, they are just one piece of the cosmic puzzle. As we continue to study these events, we are also learning more about the broader context in which they occur. The merger of black holes and neutron stars is closely tied to the formation and evolution of galaxies. In some cases, the collision of two black holes or two neutron stars may be the result of a larger galactic interaction, such as the collision of two galaxies. Understanding the dynamics of these mergers and their connection to the larger cosmic structure is an ongoing area of research. By studying the gravitational waves from these events, scientists hope to learn more about the forces that shape galaxies, the role that black holes play in galaxy formation, and how the universe as a whole has evolved over time. Gravitational waves are also providing us with a unique opportunity to study the very fabric of spacetime itself. As the waves propagate through space, they cause tiny distortions in spacetime, stretching and compressing the distances between objects. These distortions are incredibly small, but they can be detected by the most sensitive instruments we have. By studying these distortions, scientists can learn more about the nature of spacetime, how it behaves under extreme conditions, and how the fabric of the universe responds to the presence of massive objects like black holes. In many ways, gravitational waves offer us a glimpse into the fundamental workings of the universe, allowing us to probe the deepest mysteries of the cosmos. The potential for new discoveries in the field of gravitational wave astronomy is vast. As our detectors become more sensitive and our understanding of black hole mergers and other cosmic phenomena deepens, we will continue to uncover new insights into the nature of the universe. The study of black hole mergers is just the beginning of this exciting journey, and each new discovery brings us closer to answering some of the most profound questions in science. From the formation of black holes to the evolution of galaxies, black hole mergers hold the key to understanding the most fundamental processes that govern the universe. As technology continues to improve, and as we observe more and more black hole mergers, we may eventually be able to answer questions that have puzzled scientists for centuries. What happens inside a black hole? How do black holes influence the evolution of galaxies? Are there other, more exotic objects in the universe that we have yet to detect? The answers to these questions may be closer than we think, and black hole mergers will continue to play a central role in our exploration of the cosmos. For now, as we continue to observe and study black hole mergers, we are reminded of the vastness of the universe and the incredible mysteries it holds. Each merger, each burst of gravitational waves, takes us one step closer to understanding the most profound aspects of our existence. The universe is full of cosmic collisions and cataclysmic events, and black hole mergers are some of the most awe-inspiring and mind-bending phenomena we can observe. As we look to the future, there's no telling just how much more we will learn about these cosmic giants and the universe they inhabit. The study of black hole mergers continues to push the boundaries of our understanding of the universe. And it's not just the discovery of these events that's significant, it's the rich information that comes with them. Each detected black hole merger has the potential to reveal crucial details about the behavior of matter under extreme gravitational forces, furthering our understanding of the most intense environments in the universe. We can begin to glimpse into regions where normal physics may break down, and where general relativity and quantum mechanics must work together in ways that are still beyond our comprehension. One of the most intriguing aspects of black hole mergers is the phenomenon of the gravitational wave. Chirp. This term refers to the unique sound-like signal emitted during a black hole merger, detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. As the two black holes spiral closer together, the frequency of the gravitational waves increases, creating a distinctive chirp pattern. This signal is one of the key features that helps scientists identify black hole mergers. The chirp-like signal occurs because the black holes are accelerating as they orbit one another, and as their orbits tighten, the frequency of the waves they emit increases, similar to the sound of a whistle rising in pitch as a car speeds past. But the true power of gravitational waves doesn't lie only in the detection of the chirp. It also lies in the detailed analysis of the signal. By measuring the frequency and amplitude of the waves, scientists can extract a vast amount of information about the masses, spins, and other properties of the black holes involved in the merger. The amount of energy released during a black hole merger is staggering, often several times the mass of our Sun, and the gravitational waves generated by this release spread across the universe, traveling at the speed of light. Gravitational wave observatories like LIGO and Virgo play a pivotal role in capturing these waves. These detectors use lasers to measure the distance between two massive mirrors separated by several kilometers. As a gravitational wave passes through the detectors, it causes minuscule changes in the distance between these mirrors. The waves are so small that they can stretch and compress spacetime by a fraction of the diameter of a proton. Despite the extreme sensitivity required to detect such small distortions, LIGO and Virgo have proven capable of identifying these ripples with incredible precision. The groundbreaking discovery of gravitational waves, particularly from black hole mergers, is reshaping the way we think about the universe. Traditionally, astronomers have relied on light to observe distant objects, whether it be visible light, radio waves, or X-rays. These observations have provided us with a great deal of information about stars, galaxies, and other cosmic phenomena. However, light is limited in its ability to penetrate dense, opaque objects, and it can be absorbed or scattered by interstellar dust and gas. Gravitational waves, on the other hand, travel unimpeded through space, allowing us to observe events that would otherwise be hidden from view. By listening to the subtle oscillations of spacetime caused by black hole mergers, we gain access to a completely new realm of cosmic events. Gravitational waves allow us to explore the dark corners of the universe, regions where light cannot reach, such as the interiors of black holes or the early moments of the universe, just after the Big Bang. This ability to observe phenomena that were previously inaccessible is one of the reasons why gravitational wave astronomy has been described as a revolution in our understanding of the cosmos. And it's not just about detecting black hole mergers. The detection of gravitational waves is unlocking new possibilities for understanding the very nature of spacetime itself. General relativity, Einstein's theory of gravity, predicted the existence of gravitational waves nearly a century ago. But observing them directly was an entirely different challenge. Their detection has confirmed that the fabric of spacetime is not a smooth, unchanging stage on which events unfold. Rather, spacetime is dynamic, capable of stretching and compressing in response to the motion of massive objects. This fundamental insight into the behavior of spacetime has profound implications for our understanding of the universe, challenging traditional notions of space and time. While the detection of gravitational waves from black hole mergers is undoubtedly one of the most exciting aspects of this new field, there is still so much we don't know. For example, the exact formation process of black hole binaries, pairs of black holes that eventually merge, remains unclear. How do these pairs form in the first place? Are they the result of a single massive star collapsing, or do they form through some other process, such as the interaction of multiple stars or the remnants of supernovae? Understanding the formation of black hole binaries will help us unlock deeper insights into the evolution of galaxies, as these systems are often embedded in larger galactic structures. Another critical question is whether the black hole mergers we are observing are all there is to see. There could be other, even more exotic kinds of mergers that we have not yet detected. For instance, mergers involving intermediate mass black holes with masses between stellar mass black holes and supermassive black holes, are still poorly understood. These black holes could help bridge the gap between the two extremes of black hole mass, and studying their mergers could provide new insights into how supermassive black holes form in the centers of galaxies. Moreover, the potential for new gravitational wave sources extends beyond black hole mergers. We might one day detect signals from other astronomical phenomena, such as the merger of neutron stars, the collapse of massive stars, or even the earliest moments of the universe itself. In fact, scientists are already working on ways to detect gravitational waves from the very first moments after the Big Bang, a period known as cosmic inflation. If we can successfully observe these primordial waves, we could learn about the conditions of the universe during its earliest moments, and perhaps even uncover clues about the origins of the universe itself. One of the most exciting developments in the field of gravitational wave astronomy is the ongoing upgrade of gravitational wave observatories. LIGO, for example, is currently in a phase of continuous improvement, with plans to increase the sensitivity of its detectors to allow for the detection of more distant and subtle events. Future detectors, such as the space-based LISA, Laser Interferometer Space Antenna, will expand our reach even further, providing the ability to detect lower-frequency gravitational waves from events such as the mergers of supermassive black holes. These advancements will allow us to probe deeper into the universe and observe more distant and ancient events. As our ability to detect and analyze gravitational waves improves, we will likely witness an explosion of discoveries. The implications of these findings are profound. Not only will they provide insights into the lives of black holes, but they will also expand our understanding of the very structure of the universe. The study of black hole mergers is one of the most exciting frontiers in modern astronomy, offering a glimpse into the most extreme and enigmatic objects in the universe. The data we gather from these mergers will undoubtedly shape our understanding of the cosmos for generations to come. Each black hole merger detected adds a piece to the puzzle, furthering our knowledge of how these cosmic giants form, interact, and evolve. We have already learned that black holes are not isolated objects but are deeply interconnected with the fabric of the universe, influencing and being influenced by the galaxies they reside in. And as we continue to observe and study black hole mergers, we will uncover even more fascinating aspects of the universe, pushing the boundaries of our knowledge and challenging our understanding of the laws that govern the cosmos. As we delve deeper into the study of black hole mergers, we must also consider the immense cosmic implications of these events. Black holes are not just mysterious objects in the vast expanse of space. They are integral players in the cosmic drama that shapes galaxies, stars, and even the very fabric of space and time. The merger of black holes is a process that doesn't just produce gravitational waves. It also releases vast amounts of energy, redistributing mass, momentum, and angular momentum across the cosmos. This energetic release is a fundamental aspect of black hole mergers, and it plays a role in the larger dynamics of the universe. The energy released during a black hole merger is colossal. It is so intense that it can surpass the energy produced by all the stars in a galaxy, albeit in a brief burst of time. This energy is emitted in the form of gravitational waves, but it can also impact the surrounding space. The distortion in spacetime caused by a black hole merger can stretch across vast distances, allowing us to detect even distant events from billions of light-years away. In this way, black hole mergers provide us with a unique tool to probe the most distant regions of the universe, offering us glimpses into cosmic events that would otherwise be hidden from our observational reach. Interestingly, these mergers can also have an impact on the galaxies that host the black holes. It's been suggested that the merger of two black holes could contribute to the growth of the supermassive black holes found at the centers of many galaxies. When black hole mergers occur in the galactic core, they can feed into the larger black hole, causing it to grow. This process might help explain the formation and growth of supermassive black holes, whose origins have been a subject of much debate. The interaction between the smaller, stellar mass black holes and the supermassive black holes could be an important step in understanding the evolution of galaxies. Moreover, black hole mergers may also provide clues about the large-scale structure of the universe itself. When we observe a merger, we are not just looking at two black holes coming together. We are witnessing the interaction of objects that are deeply embedded in the fabric of spacetime. The way these black holes behave during a merger can tell us about the properties of spacetime itself, offering insights into the fundamental nature of the universe. Scientists believe that black holes and gravitational waves could provide a unique window into understanding quantum gravity, a theory that attempts to unify general relativity and quantum mechanics, two of the pillars of modern physics. In fact, one of the most profound aspects of black hole mergers is their potential to reveal information about the mysterious nature of dark matter and dark energy. While these two phenomena remain largely elusive, the way that gravitational waves propagate through the universe could offer indirect evidence of their presence. The detection of gravitational waves from black hole mergers could provide clues about the distribution of dark matter in the universe and help scientists learn more about how dark energy influences the expansion of the cosmos. As we move forward in this new era of gravitational wave astronomy, the technology and techniques for detecting and analyzing these signals will only improve. This means that we are likely on the verge of discovering even more profound insights about the universe. With future observatories such as LISA, which will be able to detect lower-frequency gravitational waves, we will have the ability to observe events that are far more distant than anything we can currently detect. This opens up exciting new possibilities for the study of cosmic phenomena, and black hole mergers will undoubtedly remain at the forefront of this research. Another area of potential exploration is the role of black hole mergers in the evolution of the universe. As we continue to detect more black hole mergers, we may start to see patterns emerging that reveal how these events fit into the larger cosmic timeline. For example, we may discover how black hole mergers are linked to the formation and evolution of galaxies, or how they contribute to the redistribution of matter throughout the universe. These observations could help us refine our understanding of the universe's history, from its formation in the Big Bang to its eventual fate. The detection of black hole mergers also has profound implications for our understanding of time itself. Gravitational waves, as ripples in spacetime, challenge our traditional views of time and space. The fact that we can detect these waves and trace them back to their source allows us to explore the very nature of time, opening up new questions about its origins, its flow, and its relationship to the fabric of the universe. Could black hole mergers hold the key to understanding time's deeper mysteries? Only time, or rather the study of these events, will tell. For now, black hole mergers stand as one of the most exciting and enigmatic phenomena in astrophysics. They offer a glimpse into the most extreme environments in the universe, where gravity reigns supreme and the laws of physics are stretched to their limits. Through the study of these events, we are not only uncovering the secrets of black holes, but we are also peering into the nature of space, time, and the universe itself. Looking ahead, we must also consider the role that black hole mergers play in the broader context of cosmic events. While these mergers are certainly fascinating on their own, they are part of a larger cosmic cycle that involves the birth, life, and death of stars and galaxies. The material that forms black holes often originates from massive stars that undergo supernova explosions, leaving behind remnants that collapse into black holes. These stars themselves are born from gas clouds that collapse under gravity, and their deaths contribute to the formation of elements that are crucial for the creation of planets and life. In this sense, black hole mergers represent a key piece of the cosmic puzzle, a final chapter in the life cycle of massive stars. These events remind us of the ongoing processes that shape the universe, constantly creating, destroying, and reshaping the cosmic landscape. The study of black hole mergers allows us to explore the fate of these stars, as well as the future of the universe itself. Black hole mergers are far more than just cosmic collisions of giants. They are gateways to understanding the most fundamental aspects of the universe. Through the detection and analysis of gravitational waves, we are gaining insights into the behavior of matter and energy in extreme environments, the nature of spacetime, and the evolution of galaxies and black holes. As our technology and observational methods continue to improve, we will undoubtedly uncover even more exciting discoveries, helping us to piece together the complex and fascinating story of the universe. The study of black hole mergers is still in its early stages, and there is so much more to learn. With each new detection, we are expanding our knowledge of the cosmos and unveiling the hidden secrets of these enigmatic cosmic giants. As we continue to listen to the chirps of gravitational waves, we will continue to uncover the profound mysteries of black holes and the universe itself, ushering in a new era of exploration that promises to challenge our understanding of the very nature of existence. As we continue to explore the complexities of black hole mergers, it's essential to dive deeper into the unique nature of the gravitational waves these events generate. When two black holes collide, they produce ripples in spacetime that travel outward at the speed of light. These waves, known as gravitational waves, distort the fabric of spacetime, and just like a stone dropped into a pond creates ripples, these waves spread out across the universe. Gravitational waves are essentially the echoes of these catastrophic events, carrying with them valuable information about their origin. For decades, scientists speculated about the existence of gravitational waves, but it wasn't until 2015 that they were first directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. The discovery of gravitational waves not only confirmed a major prediction made by Albert Einstein in his general theory of relativity, but it also opened an entirely new way of observing the universe. Instead of relying solely on light, radio waves, or other forms of electromagnetic radiation, we can now detect and study the universe through these ripples in spacetime itself. The first detection of gravitational waves came from a black hole merger that occurred approximately 1.3 billion years ago, far beyond the reach of our most powerful telescopes. This detection, dubbed GW150914, was a game-changer. It marked the first time we were able to directly hear the cosmic dance of black holes colliding, and it offered us an entirely new perspective on how to study the universe. This event was not just a confirmation of Einstein's theory, it was a window into the most extreme environments we could ever hope to observe. What makes gravitational wave observations so unique is that they carry information about the very objects responsible for generating them, such as the masses, spins, and the dynamics of black holes. These signals, although faint by the time they reach Earth, are remarkably detailed, providing us with a snapshot of the merger process. We can even measure how the space between us and the source of the waves is stretched and compressed during the merger. This is like hearing the details of a thunderstorm from hundreds of miles away, yet the information we can gather is incredibly rich. The detailed study of gravitational waves from black hole mergers can reveal critical information that would otherwise be impossible to obtain. For instance, they allow us to probe the properties of black holes with unprecedented precision. By analyzing the gravitational wave signal, we can learn about the size and spin of the black holes involved in the merger, the dynamics of their interaction, and the energy released during the event. Such data is crucial in confirming our theoretical models and advancing our understanding of the behavior of matter under extreme gravitational forces. Another important aspect of gravitational wave astronomy is that it enables us to study mergers that occur in distant galaxies, ones that are so far away that light from the event has not had enough time to reach us. This allows us to explore the universe at a different wavelength, one that doesn't rely on visible or even infrared light, but rather on the most fundamental aspects of spacetime itself. It's a completely new way of seeing the universe, one that transcends the limitations of traditional astronomy. But as fascinating as these discoveries are, there's still much to uncover. We've only just scratched the surface of what gravitational waves can reveal. With each new detection, we learn more about the variety of black hole mergers that occur in the universe, from stellar mass black holes merging to form intermediate mass black holes, to the rare, but still possible, mergers between black holes of vastly different sizes. These mergers help to paint a picture of the diversity of black hole populations and the dynamic processes that govern their interactions. For example, scientists are particularly interested in understanding the mass distribution of black holes in the universe. Many of the black holes detected through gravitational wave observations are significantly more massive than those we typically see in our own galaxy. The largest black holes observed are around 40 times the mass of the Sun. But there's a strange gap in the population of black holes. Few are observed to be in the intermediate mass range. This discrepancy has puzzled astrophysicists, and it is hoped that more gravitational wave detections will help us better understand why this gap exists, and what it means for the formation and evolution of black holes. Moreover, there's the fascinating question of whether black hole mergers might be linked to other cosmic phenomena, such as the formation of gravitational wave bursts, or even gamma-ray bursts. When black holes collide, they can produce intense electromagnetic radiation, and some of these events have been associated with gamma-ray bursts, short bursts of high-energy radiation that are among the most powerful explosions in the universe. Could black hole mergers be a driving force behind these bursts of energy? Researchers are actively studying this possibility, as the connection between gravitational waves and electromagnetic signals could help uncover even more secrets about the universe. At the same time, there are some profound mysteries still surrounding black hole mergers. For instance, we still don't fully understand what happens in the final moments of the merger. When the two black holes are spiraling toward each other, they release a tremendous amount of energy in the form of gravitational waves. But what happens when they finally collide and merge into a single, larger black hole? The process is still somewhat mysterious, and scientists are working hard to build better simulations and models to explain the complex dynamics of this process. In particular, they are eager to understand how the spins of the two black holes influence the outcome of the merger, as the interactions between the two rotating bodies can significantly alter the properties of the final black hole. The detection of more black hole mergers could also answer some of the remaining questions about the origins of supermassive black holes. These massive objects, often weighing millions or even billions of times the mass of our Sun, are thought to reside at the centers of most galaxies. But how do they form? While many theories suggest they grow over time by accumulating matter, either through the accretion of gas or by merging with other black holes, we still don't have a clear picture of the precise mechanisms behind their growth. Observing black hole mergers could offer crucial clues about how these giants form, grow, and interact with their host galaxies. In addition to black holes, gravitational wave astronomy has also led to the discovery of other fascinating phenomena, such as the merger of neutron stars. Neutron stars are the remnants of massive stars that have exploded in supernovae, and like black holes, they are extremely dense objects. When two neutron stars collide, they can produce gravitational waves, and these events also have the potential to release huge amounts of energy, sometimes in the form of electromagnetic radiation such as gamma-ray bursts. These mergers can also lead to the formation of heavy elements like gold and platinum, providing a crucial link between gravitational wave astronomy and the study of the origin of elements in the universe. Despite the immense progress made in gravitational wave astronomy, there's still much more to discover. With upcoming upgrades to LIGO and the construction of new observatories, such as the European Space Agency's LISA mission, we will be able to detect gravitational waves from even more distant sources. This will allow us to observe more black hole mergers, understand the properties of these cosmic giants in greater detail, and unlock the secrets of the universe's most extreme environments. In the coming decades, gravitational wave astronomy promises to revolutionize our understanding of the universe, providing us with a new way to explore the cosmos, uncover the mysteries of black holes, and gain insights into the fundamental nature of spacetime itself. Through these cosmic collisions, we are not just learning about black holes, we are learning about the very structure of the universe, the forces that govern it, and the profound mysteries that lie at the heart of existence. As we continue our journey into the world of black hole mergers and the discoveries brought forth by gravitational wave astronomy, we must consider the technological advancements that have made all of this possible. The ability to detect and analyze the faintest ripples in spacetime is a feat that required decades of development and collaboration among the brightest minds in the field of physics and engineering. One of the key breakthroughs in gravitational wave detection came with the creation of LIGO, Laser Interferometer Gravitational Wave Observatory. LIGO's design is both intricate and brilliant. It works by using two long arms that form an L shape, each several kilometers long. Inside each arm, a laser beam is split into two parts, which are then reflected off mirrors positioned at the ends of the arms. When a gravitational wave passes through the detectors, it slightly stretches or compresses space itself, causing the length of one arm to change ever so slightly, while the other remains unaffected. This small shift in distance is enough to detect the passing wave, and by comparing the results from both arms, scientists can determine the direction and strength of the wave. The level of sensitivity required to detect gravitational waves is extraordinary. The distortions in spacetime caused by black hole mergers are minuscule, smaller than the width of an atomic nucleus, and yet LIGO has managed to detect these fluctuations with incredible precision. In fact, the LIGO detectors are so sensitive that they can measure changes in distance as small as 1/1000th of the diameter of a proton. This level of sensitivity means that even the faintest gravitational wave signals from billions of light years away can be detected, providing us with insights into events that occurred long before humans walked the Earth. LIGO's success is not only due to its advanced technology but also the painstaking efforts of the researchers who have worked tirelessly to eliminate noise and interference from the environment. Any tiny vibration or fluctuation, whether from seismic activity, traffic, or even nearby machinery, could overwhelm the delicate signals from distant black hole mergers. For this reason, LIGO detectors are housed in remote locations where environmental noise is minimized. The two LIGO observatories, located in Hanford, Washington, and Livingston, Louisiana, are far from major cities and industrial areas to ensure the highest level of sensitivity. Even with the best technology and methods in place, LIGO wasn't immediately able to detect gravitational waves upon its first operation. The early years of the observatory's existence were spent refining the instruments, improving sensitivity, and testing different configurations. It wasn't until 2015 that LIGO made its first major breakthrough with the detection of gravitational waves from a black hole merger. This momentous discovery was the culmination of years of preparation, collaboration, and innovation, and it solidified the idea that gravitational wave astronomy had the potential to revolutionize our understanding of the universe. Following the first detection, LIGO continued to detect additional black hole mergers, further validating its capabilities and providing new avenues for research. These detections provided the scientific community with the opportunity to study black holes in ways that were previously unimaginable. Each new observation has refined our models of black hole behavior, as well as the processes that govern their formation and evolution. In addition to LIGO, future missions are set to expand our understanding of black hole mergers and gravitational waves even further. One such mission is the Laser Interferometer Space Antenna, LISA, which is a joint project between the European Space Agency, ESA, and NASA. Unlike LIGO, which relies on ground-based detectors, LISA will be a space-based observatory designed to detect gravitational waves by positioning 3 spacecraft in an equilateral triangle configuration in space. This design will allow LISA to detect lower-frequency gravitational waves, particularly those produced by massive black hole mergers, supermassive black hole binaries, and even other cosmic events like neutron star mergers. LISA's ability to detect lower-frequency gravitational waves is an exciting prospect for researchers. These waves have longer wavelengths and are typically generated by larger-scale cosmic events, such as the mergers of supermassive black holes at the centers of galaxies. The ability to study these larger-scale phenomena in more detail will provide crucial insights into the formation and growth of supermassive black holes, as well as the role they play in galaxy formation and evolution. Moreover, LISA will also help to probe some of the deepest questions about the nature of gravity and spacetime itself, offering a unique perspective that complements LIGO's ground-based observations. As we push the boundaries of gravitational wave astronomy, new questions arise. For example, what are the limits of black hole mergers? Can we expect to observe more exotic events in the future? One fascinating aspect of black hole mergers is that they have the potential to reveal hidden features of spacetime that were previously thought to be out of reach. For instance, black hole mergers could shed light on the elusive nature of quantum gravity, the theory that aims to unify general relativity and quantum mechanics. Some scientists speculate that the final moments of a black hole merger, when the two objects are on the verge of merging into a single entity, could reveal subtle quantum effects that might lead to a deeper understanding of the fundamental forces of nature. There is also the intriguing possibility that black hole mergers could unlock the mystery of dark matter. Dark matter is a mysterious substance that makes up a large portion of the universe's mass, but cannot be directly detected by conventional methods. Some researchers have suggested that black hole mergers may provide indirect evidence of dark matter through the gravitational waves they produce. If we detect unusual signatures or patterns in the gravitational waves, it could indicate the presence of new, unknown particles that make up dark matter. This is a tantalizing possibility that could radically change our understanding of the universe. Another question that arises is whether there is a final form for black hole mergers. In other words, after two black holes merge, do they eventually form a stable object, or could there be further mergers and transformations? The answer to this question could reshape our understanding of black hole evolution and the ultimate fate of these mysterious objects. As we collect more data from black hole mergers, the possibility of discovering even more exotic behaviors or outcomes becomes increasingly likely. In addition to these fundamental questions, black hole mergers raise important philosophical and theoretical concerns. For example, the study of black holes and their mergers brings up the concept of the information paradox. According to the laws of quantum mechanics, information about the state of a physical system cannot be destroyed. However, black holes seem to violate this principle, as anything that falls into a black hole is seemingly lost to the rest of the universe, with no way to retrieve it. This paradox has led to numerous debates about the true nature of black holes and the possibility that the laws of physics may need to be revised to account for these strange and seemingly paradoxical phenomena. Ultimately, the study of black hole mergers is more than just an exploration of cosmic collisions. It is a journey into the heart of the universe itself. These events challenge our understanding of space, time, and gravity, offering us glimpses into realms that we could previously only imagine. As we continue to detect and analyze gravitational waves, we are on the brink of unlocking some of the most profound mysteries of the cosmos. With each new discovery, we are not only expanding our knowledge of black holes but also pushing the boundaries of science itself, revealing the deepest secrets of the universe and our place within it. As we look toward the future, the potential for breakthroughs in black hole mergers continues to grow. The detection of gravitational waves has opened a new window into the cosmos, and each new discovery brings us closer to answering some of the most fundamental questions in physics. While we've made incredible strides in understanding the nature of black holes and their collisions, the universe still holds many mysteries that remain just out of reach. One area that is particularly exciting for researchers is the study of binary black hole systems. These are pairs of black holes that orbit each other, and when they merge, the resulting gravitational wave signals provide a wealth of information about their properties. By studying these signals in detail, scientists can learn about the masses, spins, and other characteristics of the black holes involved in the merger. Each detection provides an opportunity to refine our models of black hole formation and evolution, giving us a clearer picture of how these enigmatic objects came to be. Binary black hole mergers are especially interesting because they challenge some of our preconceived notions about how black holes form. For decades, the prevailing theory was that black holes are the end result of massive stars that collapse under their own gravity. However, the detection of binary black hole mergers has revealed that some black holes are much more massive than we would expect from the collapse of individual stars. These massive black holes, sometimes referred to as intermediate mass black holes, could be the product of multiple black holes merging together over time. This discovery opens up new possibilities for how black holes may grow and evolve, and it could provide insights into the formation of supermassive black holes at the centers of galaxies. The study of these mergers also has profound implications for our understanding of the fabric of spacetime itself. Gravitational waves are a direct probe of the warping of spacetime caused by massive objects like black holes. By analyzing the waveforms of black hole mergers, scientists can test Einstein's theory of general relativity in extreme environments, where the effects of gravity are incredibly strong. The fact that we can observe these phenomena from such great distances, with such precision, is a testament to the power of modern science and technology. But black hole mergers are not just important for what they can tell us about black holes. They also provide valuable insights into the larger-scale structure of the universe. Gravitational waves can act as cosmic messengers, allowing us to observe the universe in a way that was previously impossible. For instance, the detection of gravitational waves from black hole mergers allows us to study the distribution of black holes across the universe. By comparing the frequencies and properties of the waves from different mergers, scientists can map out how black holes are distributed in space and how they interact with their surroundings. This information is essential for understanding the evolution of galaxies and the role black holes play in the formation and growth of large-scale cosmic structures. Moreover, gravitational wave astronomy is also opening up a new frontier in multimessenger astronomy. Traditionally, astronomers have relied on electromagnetic signals, such as visible light, radio waves, and X-rays to observe celestial objects. However, gravitational waves provide a completely different type of signal that is not affected by dust, gas, or other obstacles in space. This means that gravitational waves can reveal information about cosmic events that might be hidden from our view through conventional methods. By combining gravitational wave data with electromagnetic observations, scientists can gain a more complete understanding of the events that produce these waves, as well as the environments in which they occurred. The potential for future discoveries in this area is immense. As gravitational wave detectors become more advanced, and as new observatories like LIGO come online, we can expect to uncover even more about the mysteries of the universe. For example, LIGO's ability to detect low-frequency gravitational waves will provide a new perspective on the mergers of supermassive black holes, which are believed to occur at the centers of most galaxies. These massive black holes are thought to play a key role in shaping the evolution of galaxies, and by studying their mergers, we can gain a deeper understanding of the processes that drive galaxy formation. But it's not just about studying black holes. The detection of gravitational waves could help us answer some of the most profound questions in science. For instance, one of the biggest unsolved problems in physics is the nature of dark matter. Dark matter is thought to make up a significant portion of the universe's mass, yet it cannot be detected through traditional means, such as light or radiation. Some researchers have proposed that gravitational waves might provide indirect evidence of dark matter. If we detect unusual patterns in the gravitational wave signals, it could point to the existence of new, exotic particles that make up dark matter. This would be a groundbreaking discovery, as it would allow us to study dark matter directly, something that has remained elusive for decades. Furthermore, black hole mergers could help us explore the fundamental nature of space and time itself. In recent years, there has been growing interest in the concept of quantum gravity, a theory that seeks to combine the principles of quantum mechanics with those of general relativity. Black holes are thought to be one of the key places where quantum gravity effects should become apparent, as the extreme conditions near a black hole's event horizon may reveal subtle quantum phenomena. By studying the gravitational waves produced by black hole mergers, scientists can test some of the predictions of quantum gravity theories and gain insight into how quantum mechanics operates in the presence of strong gravitational fields. The study of black hole mergers also has implications for the future of space exploration. As we continue to observe and analyze gravitational waves, we are learning more about the extreme environments of space, where gravity is the dominant force. This knowledge could help inform future missions to study black holes and other extreme cosmic objects. For example, the next generation of space telescopes and probes could be designed to observe the region around a black hole's event horizon, providing direct images of these enigmatic objects. Such missions could help answer questions about the very nature of black holes, their formation, and their role in the evolution of the universe. Moreover, the study of black holes is increasingly being integrated with our understanding of other cosmic phenomena. For example, the merger of black holes may trigger the release of powerful bursts of radiation, such as gamma-ray bursts, which are some of the most energetic events in the universe. These bursts can provide valuable information about the environments surrounding black holes and offer insights into the physics of extreme conditions. By studying both the gravitational waves and electromagnetic radiation produced by these events, scientists can develop a more comprehensive understanding of the processes that drive these cosmic explosions. In the long term, the study of black hole mergers and gravitational waves may offer clues to some of the most profound questions in science, such as the ultimate fate of the universe and the nature of time itself. As we continue to explore these phenomena, we may uncover new insights into the structure of spacetime, the forces that govern the cosmos, and the fundamental laws of physics. With each new discovery, we come closer to unraveling the mysteries of the universe, and the study of black hole mergers stands as one of the most exciting and promising frontiers in modern science. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.